Scudem 2025 Problem A. It is raining space dust. Presented by team number 1046. Mallory Carden, Langston Smart, and Jackson Williams. Our coach was Dr. Sarah Eskew. We are from the University of Tennessee Southern. The phenomenon of cosmic dust is when tiny pieces of comets, meteors, or asteroids break off from the main body and fall down towards Earth's surface. We were asked to find how these particles found on the Earth's surface can be used to better help our understanding of the phenomenon. We want to examine and predict what might happen to small particles as they enter Earth's atmosphere. We want to find an initial estimate of what happens to different sized particles with different velocities as they fall through Earth's atmosphere, and then finally find a possible means of estimating the distribution of the particles. Cosmic dust consists of fine, small particles of solid matter that exist on Earth and in outer space. The cosmic dust is created by explosions of stars, collisions of asteroids, or other astronomical events happening. Each year, more cosmic dust particles are entering Earth's atmosphere and making its way down towards the Earth's surface. There is approximately 5,000 to 6,000 metric tons of cosmic dust falling toward Earth every year. This phenomenon has sparked many studies into finding out why and how we can represent the data found. The assumptions made to help us solve the problem are listed below. Gravity is a constant of 9.81 meters per second squared. The dust does not encounter any other dust pieces or any other object on its way towards Earth. All dust is in a perfect spherical shape, and the particles enter Earth's atmosphere vertically. Presented here are the equations that we used. The main variables that we used were sea level air density, scale height, which we found to be approximately 8.5 kilometers, the drag coefficient, the altitude, the velocity, the temperature, the heat transfer coefficient, the heat transfer efficiency for ablation, the heat of vaporization, which was found to be approximately 6 times 10 to the 6 joules per kilogram, and then finally the area of a sphere, to which we used the formula pi times radius squared. When taking those variables, we were able to use them to come up with equations to represent atmospheric density, motion of the space dust, temperature, and ablation. Using Euler's method, we were able to come up with multiple graphs. The graphs presented show the relationship between velocity and altitude, as well as temperature and altitude. The measure of diameter for both graphs are 1 micrometer, 10 micrometers, 100 micrometers, and 1,000 micrometers, which is the equivalent of 1 millimeter. In the top graph, we can see that the purple line, which represents the 1 micrometer particle, is able to travel further than the rest of the particles. This shows that the smaller the particle, the more its velocity will increase before it starts to slow down, allowing it to travel closer and closer to the Earth's surface. The bottom graph then shows how the bigger particles will begin to move faster, which results in higher temperatures, causing them to have a higher decay rate. This means that the smaller particles, which move slower, are once again able to get further towards the Earth's surface. As the simulation shows, the smaller the dust particle, the more likely it is to reach Earth. If the dust particle is larger, it has a greater possibility of vaporizing while still in the atmosphere. As seen above, if the particle has a radius less than 1 micrometer, there will be no ablation and it will just drift down towards the surface. If the particle has a radius of 10 micrometers, it may melt, but should still survive its journey. If the particle has a radius of about 100 micrometers, then there begins to be significant ablation and the particle will begin to be partially vaporized. If the particle has a radius of 1 millimeter or greater, then there is strong ablation and the particle is likely to be fully vaporized before it can reach the surface. To get an estimate of the probability of incoming particles surviving through Earth's atmosphere will come from integrating the ablation rate across the atmosphere in simplified form. If there is data on a particle size distribution, then an attempt at reconstructing the original entry distribution using the function for the surface and then rewriting and rearranging it to get the function of the entry. This can then allow us to model the survival probability for the space dust as it falls through the atmosphere. As seen here, the function of entry will decrease exponentially as r prime increases. This means that as the function of entry decreases when we account of the altitude of r prime increasing as well as the velocity increasing. This means that the faster or higher altitude particles will lose the energy faster and contribute less to the overall flux. Simply put, slower, lower altitude particles will be able to reach Earth's surface. Thank you for listening to our presentation. We would like to thank the University of Tennessee Southern and Scudem for allowing us to participate in this competition. We used PowerPoint to make the slides and MATLAB to make all the graphs. Our references that we used for our research can be seen down below. Thank you again from team number 1046.